It's episode 6, and this time we'll be adding new Verilog code to make our tilemap display work on the MiSTer. And we'll see how to implement ROM chips in Verilog. Okay, so here I've got 3 files. Files that we were using for the last episode, episode 4, where we're doing some Verilog. And we have a new file. We got a ROM file that we're going to need to implement. We've got our tank bfpga.v, and we've got our ttl chips.v. And I've added some TTL chips that we needed from the last episode, from the actual breadboard. So let's just look at what we had from the previous one. So we had our 74LS74 chip, that's still there. Have our LS107 chip, which subscriber James had actually mentioned that in this code here, in my always block, I had not had a begin and end statement. So I've modified that there. If we look at, there's a good website called chipverify.com, and it describes always blocks and the syntax basically that is good to use with them. You can use an always block with an event, and it can be a single statement, or you can have multiple statements in between a begin and end block. And the event is typically a sensitivity list. So if A or B, so this could be always positive edge clock or negative edge reset, then begin and do a load of things, and then end. So in my code, I didn't have the begin and the end. It seemed to be okay because we were just having this statement here, which was seen, I guess, as one single statement, but it is definitely best practice to include the begin and the end. So I've added that there. We have the 74LS161, which we know is the counter, so no change to that one. But then we are adding the chip, the 74LS273, which is the octal D flip-flop with clear. So it's just like a flip-flop chip that we've seen before, but there's 8 of them, and it's got a reset or clear. So how are we doing that one? Well, we've got an input of D, and it is 8 bits wide. We have the input of the clock, input of the reset, and then an output register Q, which is also 8 bits wide. So we've got an always block, positive edge clock or negative edge reset begins. Then if the reset is applied, now don't forget here I'm reversing that, because in the real world, chip enables and resets typically like to be negative. By reading into that, I gather it's to do with the fact that it's easier to have a chip resting at 5 volts, and therefore taking it down to 0 volts is a better state to do a change, rather than it always resting at 0 volts and going up to 5 volts to be that change. So hence you'll see in hardware when you chip enable, you're typically doing a negative or a 0 chip enable rather than a 5-volt chip enable. So here we go with that one. So we take that in, and we want to check for a 1. So if we want a 0, we have to make that opposite. So if that is enacted, then the queues are all set to be 0. So all the outputs are put to 0 if reset. Else, it's set to the queue. The output is set to what the input is. If there's a positive edge of a clock. So pretty simple on that one. If we skip down to the 74LS174, that is the hex version of the octal one we've looked at. So hex, there's 6 of them. Hence the input and outputs are 6 bits wide, not 8 bits wide. So exactly the same here, just it's 6 bits wide. Then we go back up to the 74LS166, which was the 8-bit shift register. So we saw from the last episode with the actual hardware that we take in an 8-bit wide input, essentially a parallel input, and then we shift out 1 bit at a time on every single clock signal, that 8 bits. So that's what this chip is doing. We've got an input clock, an input load, an input in, which is 8 bits wide, and an output, which is 1 bit wide. Now, one thing to note here is it's not a full implementation of a 74LS166 because we're only doing the parallel in, a serial out. There is actually the opposite as well. There's a serial in and parallel out, which is the full functionality of that chip, but we're not actually doing that. So if you are going to use this code in something else, remember that it's not fully implemented. So what do we do here? So we're going to have a temporary register called temp. We have an always block with a positive edge trigger of the clock. So we begin, it says if load is initiated, so load is, again, it's a 0 state to load it, so we make that opposite to be a 1 for the test. Then temporary is equal to the 8-bit wide in, else temporary is shifted. So how we shift this is we do a concatenation of 6 to 0, which is 1 bit lopped off the top, and then we make the lowest bit a 0 bit. So it's effectively moved everything 1 to the left, so made everything a bit higher. So the output is the serial bit, is the highest bit of the temporary register, so it's that 7th bit. So that's effectively that one. Then we've got the 74LS139, and that is a 2 to 4 decoder or demultiplexer. So effectively what this one does, as we saw from the last episode, is we have a selector A and B, 2 selector bits, an enable pin, and then an output which is 4 bits wide. So if the input enable pin is low, then that is going to be listening, if you will, to the A and the B bits. If that is high, then it's not going to be doing anything. So how we're implementing that one is we're just going to do a simple assign statement. So assign Y, the output, has 4 states, and here are the tests to make those states. So all of these have the enable pin needing to be low. Obviously we're making those opposite here. So if the enable pin is low and we have a low A and a low B, then the lowest output bit is also low, all the rest are high. So in this particular chip, effectively we're using it as a chip enable. It's an address decoder. So we're interested in one of these bits being low, which we then attach to a memory chip. So this first one, if A and B are low, then the first bit of the output is low. On the next one, if A is high but B is low, then we have the second bit being low. If A is low but B is high, then we have that third bit being low, and if both A and B are high, then that fourth bit is low and the rest are high. So that's how it selects the chip in this particular configuration. So that's the TTL chips file. The next to talk about is the ROM file. So this is totally new, and as you saw in the previous episode, we've got two ROM chips that are being used. We've got the character ROM chip, which is a 2716 chip, EEPROM chip, and we've got the PROM chip, which is the color PROM, which is a 7052, or there are some alternatives to that, and that is addressing to 256 locations, and only is 4 bits wide, so it was a nibble in terms of output. So I'm going to show you how we create these ROM items in Verilog. Now it's quite important that we set them up correctly, because what we're trying to do here is make sure that that any memory we create in Quartus is being recognized as block RAM in the FPGA. So there's a special section of the FPGA that is for memory, and if it can understand that it is memory in the code, it will allocate that area to memory. If it can't do that, it's going to use up valuable logic gates to create those memory arrays, and we don't want to do that because we'll end up losing space on the FPGA for something that we could use for proper logic. So as long as we set it up in a certain way, it's going to recognize it as block RAM. So there's a few ways you can do this. One, in Quartus you can actually you can use a wizard or a template to create a RAM or a ROM, and you can have single or double input output for that, or you can do something like this where you're doing it by hand but you're doing it a certain way. So this particular way was originally, I did use a template, but then I've modified it a little bit, and I know that if you set it up this way it will be recognized by Quartus as block RAM for an FPGA. So what have we got? We've got an 11-bit wide address to give us our 2K. In size, we've got an input clock. Now it's important to mention that for actual hardware memory, that's asynchronous, so there's no clock for actual hardware memory. But for block RAM in FPGA, it needs to be synchronous. So we do have this bit of a headache of introducing a clock. What is a good way to get around this is to make the clock something very fast, in terms of like a system clock or something, where you're effectively not really dealing with a clock that's as slow as the CPU, but something that is being clocked very fast, and then can be almost seen as asynchronous, even though it is synchronous. So we've got the clock, we've got a chip select, which is low. So when it's that's why it's N chip select. It means it's active low. And then we've got an output Q, which is 8 bits wide. So we're declaring our ROM variable here, and so we're saying register is 8 bits wide, and it has 2048 locations, so 2047 down to 0. So that's how big it is. So that gives us our 2K. Then we're creating this initial block, an initial begin, which is actually reading a file. So it's read memory in hex from this file rom2k.txt and put that file into this ROM array. So once this is read, it will put the information from a file that we've yet to set up into this array. And then whenever we have a positive edge of the clock, it says, are we chip enabled? If we're not chip enabled, then just don't do anything. If we are chip enabled, then look up the address that we were given as an input, look into this ROM area for that particular address, and output the queue, the 8-bit wide output data stream for that particular address. So it's pretty simple, and I'll show you how we set up this file manually in a second. If we look at the PROM chip, it's exactly the same, but it's much smaller. So we've got an 8-bit wide address for this one. We've still got the clock, we've got the chip enable, which is low, and then we've got an output which is only 4 bits wide. When we're declaring this ROM variable this time, obviously only 4 bits wide, 3 down to 0, and 256 locations, so 255 down to 0. This time we've got a different name for our file, but we're still doing read memory in hex, putting it to the same ROM. And then the same always block, if we are chip enabled, then take the address, find out where in this particular array it is, output it to queue. Okay, so the next thing to mention is that for the Tank Battalion game, we have 6 ROMs in the actual game. Now we have these 4 ROMs are the game ROMs. D is the one that it first goes to. On the next episode we're going to look at what happens with the CPU when you do a reset, and basically what it does is it looks in a high part of the memory. So the game starts here in this particular ROM, and then it starts doing the rest of it in 1, 2 and 3. This 2K is the character ROM that we programmed in the last episode, and this one here is the memory, is the color PROM, so it's much smaller. So we're going to see how we take this particular data and we make it into a file that can be read pretty simply by this particular method. So we've got 2 bits of software here. We've got HXD, which is a hex reader and modifier editor, and then we've got this thing called Notepad++, and this is a particular text editor that can do something that I need to show you, can transpose data. So what we're going to do is we're going to open, let's do the PROM file because it's quite small. So let's open this particular file here. Now, where do we get these files? We get MAME ROMs from anywhere you can get MAME ROMs. You need to do a search, and in this one it's Tank Battalion MAME ROM, and it'll be tankbat.zip that you'll download, and there'll be these 6 files inside that zip file. So we open that one, and you can see here we've got the 256 locations. We've seen this before, we saw it in the last episode. This is telling us what colors we're getting for every single pixel on the screen. So to get this into a text file that can be read manually, what we do is we say view bytes per row, and we want to change that to 1, and then we want to do view visible columns, we just do hex, and then we do edit select all, and we copy, and then over here we paste. Now, so we can see it's put all that data in one single line. Now what we need is those need to be going downwards rather than in one single line. So we need to do a search and a replace, and in this find what, we want to press the space bar. So for every space we want to replace it with a carriage return, and a carriage return is the \n. So we'll go over here and we'll say replace all, and that's done. We can close that. It's alright over to the left over here, and you can see we have our file, and it's got the same hex numbers, and they will go all the way down, and that will be easily read then properly by that ROM file. So we save that as the same as we had. So we've got prom3l.txt. So you want to save that, and that goes in the same folder as our Tank FPGA. Now another thing to mention is that this is the manual way to do it, and what you will see is obviously with the MiSTer project we have the MRA files, and we want to have an ability to not have the core actually having the ROM file embedded. If we do it this way, what will happen is when we compile it, it will actually embed all of this ROM data in the core, and that's useful because obviously we don't need a ROM file, but if we get into trouble in terms of rights for the ROM files, because technically we shouldn't be redistributing the ROMs, and therefore we're at risk that our cores are now illegal. So we want a way to separate the ROM file from the actual core, and how the guys have done it is create this MRA file which tells the core how to access that particular ROM data. So towards the end of the project we'll have to start implementing that system instead of this, but in terms of understanding what we're doing in terms of getting the data from the ROM file into the core, let's do it this way to start with. It'll be a bit easier to understand how it's working. Alright, so that's the ROM file. Then the last thing up is what changes did we make to the Tank FPGA file. So the first thing that we've done is we've added a button user, and what we're going to do is we're going to change the characters on the screen by pressing this button user, and lower down this file you'll see how we're doing that. All the rest of the inputs are the same as they have been. We've added a new section here, new wires and registers. So the first one is, we are, from the last episode you remember we had a dip switch that had 8 bits wide, and that's how we were selecting the characters on the screen that we wanted. So we're starting off here saying that the register is 8 bits wide, and it's got this particular pattern of bits, and this gives us a specific character. Later on we will see that down here we've implemented, whenever there's a negative edge of this user button, then we're going to add 7, the number 7, to that, and that will therefore give us another number, and each time we have a different number we have a different input and we'll get a different character. So it's quite elegant way of just changing what we have on the screen. Okay, so we are adding a few items for the chips. So these are just wires, either let's say arrays or single wires that we need as outputs or inputs to those chips that we're going to add. The clock and everything is all still the same, so we can go down to the timers are all the same. The vertical blank is fine. So we have added this screen render 3 and screen render 4, and then screen render 1A. So that's effectively what we've added, and I'll talk through that. So it's effectively what we've done. Well, one thing we've done is, from the last time that we did this code, I've changed the V blank from a positive output to a negative output. I did kind of mention this. It was before, when it was all Verilog, the V blank was effectively triggering when it was low, let's say. So as I've said before, these chips are all the other way around. So we enable all of these chips when they're low, not when they're high. So we want to do the exact opposite with our V blank than we had before, because we're going to mimic from this point on real chips. So this V blank now goes high when we don't want it to be active, and it goes low when we do want it to be active in terms of the screen. So we can do that by changing whether it's coming out of the negative, positive or 0 way. So we're implementing the 273 here, which is the octal flip-flop, and we're putting in the input from our dip switch. We've got our clock is H4, and then we have a pull-up resistor for our reset, and then the output goes to L2Q, which is just a Q output name for this. Then we've got our ROM chip. So for the address, you remember we had the top 6 bits, however many bits there were, of the L2Q, and then we had an additional V4, V2 and V1. So that we are concatenating that in these curly brackets to make that the right length. We have a clock input because, as I said, we need to make this synchronous. Now you'll notice we're using clock, which is actually a fast clock. So you know, it's going to be so fast. It's the 18 megahertz clock. We're not going to see much difference with using that, but it's going to make it a synchronous clock. With this one here, we're basically enabling it all the time. So our chip enable is set to 0, so it's always enabled. When we get further into the project, we're going to not always have that enabled. We're going to actually connect it to the 6502 chip and have it enabled only half the time. The output is just a label, so we've put it as K2 D in this case, or Q, but that's the label I've given it. And then we can connect that up to the 166, so that is the input there. So onto the 166 we have our clock. We know that the clock in the 166 is the 6 megahertz clock, which comes out of one of the timers that we had previously. Our load is from the chip C411, and C411 we have specified up here. So this is quite an important one. You remember from the last video, C411 was like a timer chip, and we need to look at the schematics to see that that is outputting from that 139. So that's the load. The input is from the K2D, which we saw as the ROM, and then the output is a single output, which we're calling J2Q. So it's just a 1-bit wide output. And then the 174, which is the hex D flip-flop, is taking the L2Q, and it's taking those, remember we saw it's taking the upper bits, so it's only taking, how we choose which bits to take is you can have these brackets here and say 7 down to 2, so we're not taking the 1 and the 0, so we're chopping the 2 bottom bits off that. The clock is again the same clock as this one up here, so it's the, or at least the load, the C411, so that was the timer that we saw in the last episode. The reset is a pull-up resistor, so we're not actually going to reset, it's permanently set to be high. And then the output is a J3, so we've created this output called J3Q, which is just the output there. And then the prom chip is, as we saw before, so the address we're choosing on this one. So if you remember, we had the J3, so the output to the flip-flop was the 6-bit wide top, so 5 down to 0, 6 bits wide. Then we have the sprite engine, which is set to 0 here, because we aren't going to implement that just now, so we'll just forget that and say the sprite part is 0. But the lowest bit is the tilemap renderer, and that's output from J2Q. So J2Q is obviously the 166, parallel to serial shift register. So hopefully that should look familiar to you in terms of the input. The clock is, again, it's making a synchronous clock where you know, there otherwise wouldn't be, so we've got a high clock. And then the V blank is what is enabling this chip or not. So that is our input, and it's active low. So when the v blank is low, we're active. When the v blank is high, there's no output from the screen. And our outputs are blue, green, red, and the red 2, which makes it a bit brighter, as we said in the last episode. And those ones then are connected down here. We're making it, the MiSTer has a 6-bit wide color, so we're just making that 6 times for each one, and then outputting that goes to the outside world, the red, green, blue VGA, and horizontal sync, which is actually composite sync in this instance. And then this 139 is just one of the other timers that we were creating. That's what was the input to this C411 up here. So that's it. So it's really just implementing that hardware that we did in the last episode, and hopefully pretty clear. If there isn't anything clear in this one, then just get in contact and we can try and make it a bit clearer. But as usual, the code will be on the GitHub for you to download and try it out, and have a look at it yourself. Okay, so I've got my Tank B FPGA latest version open in Quartus. I've already compiled it to save some time. So what we're going to do is we're going to go to Programmer. Now the MiSTer is already on, so we are detecting everything just fine. Remember, if you forgot to turn the MiSTer on or whatever, you might need to go to Hardware Setup and refine this one, or you might need to add a file or whatever. But if start's ready there and not grayed out, then we're all good. So what we'll do is we'll press start, and then we should have something on the screen. So all is good. Okay, so when we first load up the core on the MiSTer, we get this pattern of M's, and then every time we press the user button, it's going to change the character to a full set of, in this case, A's, just some bits of wall, and just random whatever we press here. We haven't implemented a debounce system on the button, so it's a bit erratic whenever we press. We could put some logic in there to only listen to it for a certain period of time, and then it would be a little less erratic. But it's just to get the point that when we press this button, we're just selecting another random character. So good, we've effectively shown we can implement a character ROM in Verilog on the screen. And that's exactly just mimicking what we did in hardware in the previous episode. So on the next one, we're going to implement setting up some other items. So we're going to have a specific pattern that we're going to put into ROM. We're going to do that on hardware first, and then we can implement that also in Verilog on the MiSTer. So it should be good fun.